Digital circuits are my favorite. I really only mean flip-flops because they're friggin' awesome. What's the answer to this? What'd you get, Ben?
All this is under one big dot.
Okay.
A dot plus C dot plus C plus B.
Okay.
And then B plus C dot and A.
Nice. Well done. Okay, so that's the answer. All right, we're going to shift gears real quick. I'm going to erase everything but this. And we're going to talk about flip-flops. So truth tables, as we've seen, have a very specific truth table. I mean, it's a very specific format. You get numbers on the left side that do stuff. I'm going to introduce the idea of a flip-flop, and truth tables are going to break a little bit, okay? Because truth tables for a flip-flop are weird. Okay, so I'm going to have a system where I have an A and I have a B, okay? And what I'm going to do is I'm going to plug this into, oh, is it a NOR or a NAND? Another thing I don't ever remember. Nope, I'm right. It's a NOR. And I got another one up here that's a NOR. And I'm going to take the output of this one, plug it into the input of this one. I'm going to take the output of this one and plug it into this one. And I'm going to have two outputs. One I'm going to call Q, one I'm going to call Q naught. Because actually Q naught is the opposite of Q. Let's draw a truth table. Actually, you know what? Before we draw a truth table, let's play with numbers. So A and B are both 0. 0 is going into a NOT switch. If let's say, assume that Q naught and Q, A and B are all 0. Okay? So output of this is 0, output of this is 0. If we're starting with A, both of these outputs are 0 because this is 0, this is 0. This produces a 1. 1 goes up here, goes into here. Because there's a 1 that goes into a NOR gate, that makes this 0. So your output here is if A and B are equal to 0, this is equal to 1, and this is equal to 0. Right? It's pretty straightforward, right? Okay, now let's go back and assume that everything is 0 again. And I'm gonna go say A and B are 0 again. But I'm gonna start up here and I'm gonna say B is 0. So we got 0 coming in. We know this is 0. So we got 0, 0. Well, this is now a 1. And we have a 1 that goes in here, which makes this be a 0. Wait, what? If A and B are both 0, we have no friggin' idea what Q and Q naught are. Nice. Because both Q and Q naught switch, depending on which direction you go through the circuit. This is what's beautiful about a flip-flop, because this is introducing the idea of memory. Okay? Let's say this system starts out with this is equal to 1, this is equal to 0, which means this produces a 1, and this is equal to 0. Okay? We're starting out with this system. Okay? A and B are both equal to 0. So we have a 1 goes into here, produces a 0. We have a 0 that goes into here. This is also 0, that produces a 1. It is now self-sustaining. As long as A and B are both 0, that system remains at Q equals 1, Q naught equals 0. Well, let's go ahead and plug weird stuff in now, because we can do that. Let's set A is equal to 1, and B is equal to 0. Okay, so A is equal to 1. Well, the output of this one is 1, which means this is 0, which means this does not change the circuit whatsoever. Okay, that's great. Well, let's say A is equal to 0, and we'll set B equal to 1. Okay, B is equal to 1. That's going to force this to be 0. Q now changes to 0. Okay, you have 0 coming in. A is also 0. That makes this be 1, which you now have a 1 that goes into there. You set B back to 0. The system now has reset such that Q is 0. If we continue to put in A equals 0, B equals 0, it's going to happen. We continue to put in A equals 0, B equals 1, we're going to continue to get this system. Now, with this system, as it is, let's say we stop caring about Q naught, because Q naught doesn't matter. Okay? We only care about Q now. I'm going to now plug in A equals 1, B equals 0 again. So we know that plugging in B equals 1 forces Q to be 0. We know that keeping B and A at 0 forces Q to stay at whatever it's at. If we plug in A equals 1, that forces this to be 0. This being 0, if B is also 0, forces this to now switch to 1. Well, this kind of a truth table doesn't make sense if we plug in A, B, Q. Well, if it's 0, Q could either be a 0 or a 1. If we get this, what this does is it forces Q to be a 0. If we get this, it forces Q to be a 1. And if we plug in, they're both equal to 1. Q goes back to 0 again. Well, that's not helpful. What is this? We're going to have two different states for the same input values. And this is where we represent something that's known as, this is called an SR flip-flop. Okay? Because instead of using A and B, the way that they actually denote this is S and this is R. Okay? And the way that we're going to write our truth table is S and R is that Q retains whatever value it was prior to that input being read. And we denote that by saying Qn is equal to Qn minus 1. Just means that it's the previous value. If we set the function, we force Q to be 1. If we reset the function, we force Q to go back to 0. And that's our truth table. We have now introduced the idea of memory, where we now have a system that remembers the state it was at. Okay? And it forces a very weird truth table to come out as a result. Flip-flops get crazier from here. This is the simplest flip-flop you can get. Well, it's almost the simplest one. Actually, the simplest one you can get is this. But you don't even know what the output of that is going to be. Because it depends on, this stores some state, but you don't know what the output of that one's going to be. This is the simplest flip-flop. This is one that allows us to control. And we can keep building on this so you can actually make more and more complex flip-flops from here. Now, the circuitry for flip-flops do get, they do get a little bit crazier from here. So I'm not going to be drawing out the actual circuits. Instead, what I'm going to do is I'm going to start representing them with just by drawing their truth tables. Okay? So, this type of flip-flop, an SR flip-flop, remembers if set. It also remembers if it's reset. Okay? That's what it does. Here, no matter what the set value is, if you reset it, the output will always be 0. If set and reset are on at the same time, reset always wins. But this is just it. It remembers if it's set, because if it sets a value and then goes back to 0, it stays on. If it resets a value and goes back to 0, it stays off. Okay? FYI, this is how memory works in a computer. There are nanoscale flip-flops at play. And this, by the way, is it's for RAM only, because ROM, which is the actual, it's non-volatile memory, does not use flip-flops. RAM does, and that's because it requires power to run a flip-flop, which is why when you shut off your system, all of your RAM is erased. Everything that was left in storage in your random access memory goes away. But your ROM does not, which is why we can hold flash drives that have no power. It's because they don't use flip-flops. They use what's called flash memory. In any case, we can start making crazier and crazier flip-flops from here. I'm no longer going to draw the circuits. Oh no, I will. I'll draw it for this one. We're going to introduce the idea of a clock. Okay, so here I've got an S. Draw this a little bit bigger. S. It's going to go into an AND gate. I've got a C that's going to also go into that AND gate. And then I got an R that's going to go into this AND gate. Okay? And then this goes into my standard SR flip-flop. Okay. Now, with this system, there is one change. And the change is, I cannot change this system if the clock is off. If the clock is off, it doesn't matter what R and S are. Okay, because this is an AND gate, it requires both S and the clock to be on in order for this to register. It requires both R and the clock to be on in order for this to register. So if your clock signal looks like this, which it does, it's a very precise square wave. If your clock signal looks like this, while it is in the off state, which is here, 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 while it is off, you cannot change the system. Your system remembers where it was when it was turned on last, and it stays off. If you have a clocking signal that turns on for a very short amount of time and then stays off for a very long amount of time, it will remember exactly what happened during the time that it was turned on, and nothing else will matter. That's the beauty of a system like this. Okay? The way that we draw the truth table for something like this is we have C, S, and R. We have our Q. If C is 0, it doesn't matter what S and R are. Q stays the same. And we just eliminated having to write out 4 different options for S and R, because it doesn't matter what they are. If the clock is off, Q stays whatever value it was at the previous iteration. Okay, now if the clock is on, then our standard truth table comes back into play. 1, 0, 1, this is equal to 0, 1, 1, 0, this is equal to 1, 1, 1, 1, this is equal to 0. Okay, same truth table, just one extra entry. It forces it to only occur when the clocking signal is on. Now this has some benefits, but this also has some drawbacks. Let's say we're dealing with a system that randomly changes S and R by accident because it's very volatile. Let's say we can only control it for a very short amount of time. And then after that, it begins going crazy. Okay, so we may be able to control it for about this amount of time, but the rest of the time the clock signal is on, S and R begin switching rapidly. And we can't control that. That becomes a problem. To which is where we can set this, but then these values sometimes may oscillate because computers are whack. Okay? Well, this introduces the idea of we need something a little bit nicer in order to figure out what's going on here. Okay? Instead of taking it for the entire time it's on, we're going to have this be called something called an edge-triggered flip-flop. Okay? All that means is that when it sees either a positive edge or a negative edge, the positive edge is when it goes up, negative edge is when it goes down. That is the only time it actually sits and looks at allowing S and R to change the system. So at that point, we have what's called an edge-triggered system. And an edge-triggered flip-flop looks very much like this. So this is just a clocked SR flip-flop. Over here, if we do an edge-triggered, we'll call it a positive edge-triggered, which just means every time the clock value jumps up, then it changes. And we'll make this be another SR flip-flop. Then the truth table looks like this. C, S, R, Q. If the clock is equal to 0, doesn't matter what this is, Q is equal to n minus 1. If its clock is equal to 1, doesn't matter what this is, Q is equal to n minus 1. If the clock is on the down edge, it doesn't matter what it is, still equal to Q minus 1. And only if the clock is changing from a 0 to a 1 does it matter, and then we draw in our standard truth table for SR, which is this is Q n minus 1, this is 0, 1, 0. Okay? So that is now an edge-triggered SR flip-flop. We have the ability to keep going with these types of things. But usually you'll only see just a standard flip-flop, a clocked flip-flop, or a positive or a negative edge-triggered flip-flop. Those are the three different types of every kind of flip-flop. Okay? Are the difference between those three, does that make sense? Anybody have questions on that? Okay. Now there's more than just SR flip-flops. SR flip-flops do not toggle at all. You can take an SR flip-flop and build something that's called a D flip-flop. Make sure I'm drawing this right. Yeah, okay. So in a D flip-flop, we're going to say it's just D. We got Q and we got Q naught. And now, instead of having an S and an R, we have a D. Now what a D flip-flop does is it toggles. And that's the most important feature of it. So in a D flip-flop, what you have is DQ. Now an ice cream. Dang it. Darn you, Warren Buffett. If D is 0, because we only have two options here. If D is 0, Q equals Qn minus 1. If D is 1, Q is equal to the opposite of what it was. That's it. Na, na, na. That's awesome. Now this poses some problems. Because what happens if I leave D on for some amount of time? Is that going to mean that Q is going to continue to toggle endlessly? And the answer to that is, we don't actually know. Which is where in a D flip-flop, you usually see it in a clocked cycle. And you usually see it as an edge-triggered clock. Because even then, if you have it on for any amount of time, it will just continue to toggle indefinitely. This is where edge-triggered becomes really, really important. So for an edge-triggered, let's do it on a negative edge this time, just for poops and giggles. A negative edge, triggered, D flip-flop. Okay, the idea here is you got a clocking signal, you've got your D, and you've got your Q. Man, I really should not do this class while hungry. I'm gonna have the biggest snack after this class. I'm gonna like just randomly eat somebody in the hallway. Okay, so the idea here is if it's 0 or 1, doesn't matter what D is, Q stays the same. But if it's on the negative edge, which is when it drops from 1 to 0, then if D is equal to 0, Q stays the same. And if it's on the negative edge, if D is equal to 1, then Q toggles. Okay, what is the difference between an SR flip-flop and a D flip-flop? D toggles. SR just remembers the value. You can set and reset it. Okay, and that is the only difference between these two. It's just this one only toggles. It doesn't do anything but toggle. It has one input for that reason. What if we wanted to combine an SR flip-flop with a D flip-flop such that we could set and reset or toggle it? That is what's known as a JK flip-flop. And everything we've done in this class has led up to this moment. Because JK flip-flop is just amazing. It's just like just saying it. Like, JK, it's a flip-flop. Yep, I put you through second differential systems just so that I could use the word JK flip-flop in front of you and you would be able to understand what I'm saying. This is why you're here, Vince. As you'll notice, every one of these flip-flops is denoted by how you label its inputs. So for a JK flip-flop, what you have is you're going to have a clocking signal. And then you're going to have your standard Q, Q naught coming out, do, 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 do. And the truth table for a JK flip-flop trying to make sure I get this right. Oh, dang it. Let's go back and say that we're going to do a positive edge triggered. JK flip-flop. And by the way, if you haven't noticed yet, the only difference between a positive and a negative edge triggered is what direction the clocking signal is pointing. So if I say positive, it just means this is an up arrow. That's it. You wanted to do a negative edge triggered, you just draw the down arrow. It's the same thing. Okay? It's the same thing. It's just get it every time. What's that guy who sells Slap Chop? Vince. Yeah, Vince. Yeah, I'm Vince from Slap Chop. I'll be slapping away your problems. So we got C, J, K, and Q. Truth table for this is, once again, if the clock is a 0 or a 1, Q just stays the same. However, if the clock is on an uprise, then what you have is if J and K are both 0, then this is the memory state, where it just remembers where it was at. Same thing we had for SR flip-flop. Here, if you have your positive edge on your clock and you issue a K but not a J, what this does is it does a reset. So this is what's known as memory. This is what's known as resetting because it sets the value to 0. If you do the other way around where you have a J and not a K, this is called setting because so far every bit of this is the same as a clocked SR flip-flop. The one difference between this and an SR flip-flop is that when you have a positive signal and both of them are equal to 1, this toggles. Okay? A JK flip-flop is an SR flip-flop that can toggle. That's it. Or you could say that a JK flip-flop is a D flip-flop that has set and reset states. That also works. Okay? You can do some friggin' awesome stuff with flip-flops. You can bake cookies with them. You make friends with flip-flops. You won't make any friends with flip-flops, I promise. Sorry. You might, Jacob, but none of the rest of us will. The rest of us is like, hey Mom, I learned about flip-flops. Son, go back into your cage. I didn't have any traumatic childhood experiences. What are you talking about? Oh man, that was dark. Yep, so that's it. You can make a counter out of these. If you have a flip-flop that feeds a flip-flop, it turns into a counter, especially if it's a D flip-flop, because it toggles on and off every time you receive an input. So here, if you have a D flip-flop connected to a D flip-flop, connected to a D flip-flop, what happens is every time this changes, goes from 0 to 1, this changes. And then you'll have a 1, and this will be a 0, 0. And then, huh? Oh no, this is in the book. Which you can read in the book, but I just think it's awesome. And no, you won't have to do any, because I'm covering this in like 30 minutes, we're not really going to be covering JK flip-flops on the test or on the quiz. So. Oh, that's also a no, because in this one you're probably not going to be using flip-flops. You're going to have to use, it's just going to be like building truth tables for your project, which that's a little bit less important. I mean, you probably could use flip-flops, but I feel like that's unnecessary levels of effort. In any case, having this, now if you were to go back and do 0, 1 again, where it goes down and up again, this one resets to 0, but it sends a signal of 1 out to here. And it would continue to propagate that signal. And that's the idea of a D flip-flop. It's actually, well, not just a D flip-flop. This is more of a, probably a JK flip-flop. But if you connect a bunch of JK flip-flops in series, you can get a really fun counter. All right, I'll see you all on Thursday. There's a quiz due tonight. There's a reading assignment due tonight. I believe there's also a homework assignment due tonight. Yeah. So just please remember, this is the last reading assignment and homework assignment. You will have a quiz due next week, and I will assign you your test